Hope you all had a great Easter. Welcome back. We have, as always, a very great and interesting webinar for you today. Before we start, just a couple of announcements. First one, and very important one, is this. Today, our great Queen, Margrethe II, is turning 80. And I thought we should just give her a tribute. If it wasn't for these Corona days, the whole city would be, Copenhagen would be packed now with people celebrating her. Unfortunately, that is not the case. So I thought we would just pay our small tribute to our great Queen here on this webinar on 16th of April. I think you agree with that, Kristian?
Absolutely, absolutely.
That's good. Okay, so, and then there's another announcement, which is, let's say, more technical relevant. It's next Thursday, April the 23rd. We'll have a special webinar, and we will be, Kristian Olsen from SuC 7 will be our guest. And he will explain about how SuC 7 use Optum G3 on some. He'll discuss some practical problems where they've used the software, and it's also not going to be only Optum. He will also mention Abacus and Plaxis, so it's going to be more a general topic of geotechnical engineering, 3D analysis in offshore. So I really hope that you'll make it. It's next Thursday, 23rd at 4 o'clock in the afternoon. And Kristian is a great guy. He's entertaining and a good speaker. So I'm sure it will be worth your time. All right. Then back to today's webinar, which is about analysis and undrained clay. And it has some kind of the same taste as our previous webinar on sand. So when you model friction materials, you might be wondering which friction angle should I use, and what about stress level dependency, stress state dependency. And turns out that with clay you have often run into a similar problem. So to kind of accommodate this, or to alleviate our users from having a hard time finding material models for modeling clay, we've developed a very good and a general model for undrained clay called we call anisotropic undrained shear model AUS that Kristian will talk about here today. And so it's going to be very nice, and make sure to ask a lot of questions during the webinar. And after, of course, as usual, you will have a chance to talk directly to Kristian. So I think with that, we should get started. Kristian, will you go ahead?
I have shared my screen. I don't know if you...
Yeah, that's great. Yeah.
Okay, great. So yeah, thanks, Jan. And as you mentioned, this webinar kind of in a way follows on from our webinar last week on sand, where we discussed the fact that the friction angle is not constant. It depends on the stress level. I mean, it depends on the density and the kind of material you're dealing with, of course. And then it depends also on the stress level and on the stress state, in the sense that the friction angle in plane strain and triaxial compression usually are different. And and it's something that you don't see in 2D, where you are always in plane strain and where you always activate the plane strain angle. But when you then go into 3D, you have to somehow make some additional considerations as to what stress states you might have there, which is of course the full range of stress states. And with clay, with undrained shear strength of clay, it's much the same. In plane strain, we have the plane strain undrained shear strength. And when we move into 3D, then the question is, what is the shear strength in undrained shear strength in, say, triaxial compression versus triaxial extension? Are they identical, or is there a difference? And that's what this webinar is about, and it's what this model that Jan mentioned, the AUS model, addresses. So just very brief introduction. So if you were to do an undrained analysis of or if you had a situation where you had a circular foundation in a clay soil and you're interested in the short-term conditions or the undrained bearing capacity and the immediate settlements, you might pick up the well-known Tresca model. So the yield surface or the failure surface is shown here, the well-known Tresca hexagon. And what I mean by the Tresca model is a simple linear elastic perfectly plastic model. So it has two parameters, SU, the undrained shear strength, and then the shear modulus. And it's a fairly crude model, but it may actually, depending on how exactly you choose the stiffness, may actually be made to fit typical sort of lab data fairly well. That's kind of an example is shown here. And of course, SU very often varies with depth. So for example, a linear approximately distribution is shown here or something like shown here. This is from, I believe, the Cowden site from the PISA project where I've taken this. So we have kind of a crust, so a higher strength at near the ground surface and then a decrease in strength at some depth and then a more gentle increase of strength with depth at some depth. So this is these types of profiles are direct input, of course, to the Tresca model, and which is quite convenient. And you can do something similar with G. You can relate it to SU in one way or another. So all in all, not really a terrible model at all, and it's of course widely used. It requires that we determine the undrained shear strength, so that can be done in situ with CPT or whatever. Or it can be done in the lab. And if we were to do it in the lab, we might set up a Tri-Axial compression test, which is sort of what I've tried to indicate here. A cylindrical sample of clay, you then subject it to a hydrostatic pressure, you let it consolidate, and then once you're ready to go, once the pore pressures, the initial pore pressures from the initial consolidation have dissipated, well, then you ramp up the vertical stress here until the sample fails, and we know and we can verify experimentally that it fails when the difference between sigma 1 and sigma 3 reach a critical magnitude. So, and that critical magnitude is what we call the undrained shear strength. SU, or I've put a subscript C here, as you can see, to indicate that this is a compression test. Because what we could do, of course, was we could run a different test. We could run an extension test. So it's the same thing. The initial sort of set preparation is the same, but then as the compression test, but then instead of increasing the vertical stress, we actually decrease it. And that, of course, will also lead to an increase in the difference between sigma 1 and sigma 3. And once that reaches a critical magnitude, then we have failure. And we indicate that by this constant here, SU, E for extension. So we have two different tests where we determine two strength parameters that may be identical or may not be identical. So that's the first question, really. Are they identical or not? And the second question is, do we really expect them to be identical? I will already reveal now the answer to both of these questions is no. But if we assume Tresca, we of course wish they were identical, because that's of course the exact assumption behind the Tresca criterion. We have identical strengths in extension and compression, but what you will see most of the time, if not pretty much all the time, is that you'll typically have a smaller strength in extension than in compression. So you will have a difference between what I call SuC and SuE. And if we assume that we are dealing with an isotropic material, well, then we have this point mirrored onto these 2 points. So this is the same triaxial extension corner as this one. And we can then draw some straight lines through the failure points. And so this gives a different failure envelope than the standard Tresca hexagon. It looks more like a kind of a more Coulomb cross-section. And that is in fact what it is. We call this criterion the generalized Tresca criterion, and it's you could say it's one step up from the standard Tresca model. It takes two parameters instead of one, so the two shear strengths in extension and compression. This is the equation for the failure surface. It involves all three principal stresses, and you can think of it as involving two parameters, or the strengths themselves, or the strength ratio, which sort of gives the shape of the surface in the deviatoric plane, and then the compressive strength, which you could say dictates the size. We wrote a paper about that a couple of years ago. So it's a kind of a pressure insensitive prism, but with a cross section in the deviatoric plane that depends on this extension to compression ratio. So that if the ratio is 1, then we have just a standard Tresca. If it becomes 1/2, well, then we have a kind of a Rankine triangle. And if we have something in between, well, then we have something in between. There is a limitation to this model. We call it the generalized Tresca modulus, as I mentioned, and that is the extension to compression ratio must be between 1/2 and 1. Otherwise, the yield surface becomes non-convex. So this model is available both in G2 and G3. It's actually just called the Tresca model, and then there's an option. It can either be the standard Tresca model, so then there's only a single SU, or you can go for the generalized one, and then there's SuC and SuE. So that's how it is. And if we look at then what is the typical extension to compression ratio, and that's kind of difficult to say because it's really quite variable. I was lucky enough to get hold of a kind of a reasonably large database of results compiled by Sky1 2013, who has taken data from all over the world and then plotted this extension to compression ratio as function of the plasticity index. I don't think you can see much of a correlation, but what you can see is that this ratio is really quite variable. And the gray area here is the area of applicability of the generalized Tresca model. So between 0.5 and 1, and you can see you can actually capture quite a lot of typical data. Tresca, a ratio of 1 is really, there's not a whole lot of data up there. So Tresca, it's not important. It's a bit of an anomaly. You typically be down here sort of on average about 0.6 to 0.8. And is there a correlation? Well, maybe with plasticity index, maybe a weak one. But I think the jury is still out on that. Now, if we look at where this actually comes from, this effect that we have different extension and compression strengths, you can think of it as coming from basically the underlying effective stress behavior. So we know that everything to do with strength and deformation of these types of materials has to do with the effective stresses. So suppose that the effective stress behavior is governed by Mohr Coulomb, and suppose that we set up a very simple linear elastic perfectly plastic Mohr Coulomb model and then did an undrained, so a coupled pore pressure deformation analysis type test. What we would find is that when we run this test, well, then the mean effective stress does not change during the test, whether it's triaxial compression or extension, doesn't matter. So if you look at it in the PQ plane, we have the extension branch of the Mohr Coulomb envelope, it's here. The compression branch is here. The slope of these two is different. And the mean effective stress doesn't change during the test. So a compression test would move right up to there, and this would be the undrained shear strength, the compressive undrained shear strength, and this one here, the extension undrained shear strength. And the ratio between the two is this quantity here, which depends then on the drained friction angle. And if you insert a reasonable friction angle, say 30 degrees here, you will find typically a ratio of about 0.7. So that's kind of what you would, this is an expected ratio. So, and this generalized Tresca model then accommodates that, where you input the undrained shear strengths directly, but it has some justification, this ratio, by analysis. If we look at what the ratio corresponds to in terms of friction angles, well, if we look at a range between say 15 and 45, we are at about 0.6 to 0.85. So probably outside of this range, it's harder to justify the model, but definitely inside this range where sort of the majority of the data somehow is, I think the model is fully justified. And you can look at true triaxial tests as well. This is a true some data from Lade, who prepared these samples so that they were really, there's no reason to believe that they were anything but isotropic. So for that's sort of the first message I wanted to get through. For a perfectly ideal isotropic material, we should expect, and we do find experimentally, a difference between the undrained shear strengths in extension and compression. So that is the first really kind of important point before we start talking anisotropy, that for an isotropic material, ideal isotropic material, there is a difference between these two strengths. So when we look at clay in 3D, we should really make reference to at least two strengths, the extension and compression strengths. And the question is, what does it mean then in terms of, say, the strength and deformation characteristics of typical geotechnical problems? Well, I've looked a bit at this tunnel face stability problem recently. So that problem involves tunneling with sort of a pressurized tunnel head. So you can want to keep this tunnel face stable, and you can stabilize that by, for example, an air pressure or some sort of pressure. So the question is, or there's sort of two questions here in this problem. The first question is kind of, you could say, an active type earth pressure problem. How much pressure is needed to keep the tunnel face from collapsing into the tunnel? That's the first question. And then a kind of passive earth pressure problem. What is the maximum pressure that you can actually apply to the tunnel face before it becomes stable the other way, before you have a so-called blowout? And so these are two different problems. Collapse is the minimum pressure necessary to keep things stable, and then the blowout is the other one. So if we look at Tresca first, and I'm just showing the collapse mechanisms here. So if we look at the Tresca, for a Tresca material, so ratio of 1, well, this is how it looks, and then you can decrease it, and you get a mechanism, you get more and more basically soil to retain, and the collapse pressure then increases with decreasing SuE to SuC ratio. What I plotted here is the extension to compression ratio versus the collapse pressure normalized by the Tresca collapse pressure. So once you get down to 0.5, well, you have an increase of about, I think, 27% or so. So it's not a huge amount it means, but it means something, and it's what it is for this particular problem. And then for the blowout problem, well, that's interesting because it turns out that the blowout pressure is completely unaffected by the extension to compression ratio. And that kind of makes sense, of course. In the collapse case, we have a lot of stress points in extension. In the blowout case, most of the stress points are in compression. So it's really problem dependent what effect an extension to compression ratio less than 1 has. If there's quite a bit of extension involved, so active earth pressure type problem, slope stability as well, then it can mean quite a bit. Otherwise, less so. Then some more predictions from the model that I just wanted to have a look at. Remember, this is a 2-parameter model where we basically input the strengths determined in triaxial compression and triaxial extension. That's these two tests here. Then in addition, a quite common experiment is a so-called direct simple shear test, where you sort of shear the material like this, and in that way infer the undrained shear strength that we could call, I call it SUS, the simple simple shear undrained shear strength. And it turns out, you can show that quite easily, that this is actually a function, assuming the validity of the generalized Tresca criterion. This is a function of course, the two other parameters. The extension and compression is basically the harmonic mean of the two. So that the simple shear strength is somewhere in between the extension and compression strengths. Here's some typical values. And the question is then, given an extension and compression strength, how well does the generalized Tresca criterion really match a measured simple shear strength? And we can look, there are a few data sets out there where all three tests have been performed. This LAD data set is quite a well-known one, where he has triaxial compression, triaxial extension, and direct simple shear. So this is the normalized undrained shear strength, so normalized by the mean vertical stress, again as function of the plasticity index. So you can see the ratio varies with plasticity index, but the ratio between, say, extension and compression is never 1. Direct simple shear is somewhere in between, as we expect. And what does the generalized Tresca prediction give? It gives something like that, which is not too bad, I don't think. It's not exactly the green line, but the green line is anyway a crude curve fit to some data that are fairly scattered. So I would consider this prediction a success. But then there are other cases, other materials where it's sort of more problematic to make sense of things in terms of the generalized Tresca criterion. Here are some data for Norwegian clays, and this shows the extension to compression ratio in blue, and then the simple shear to compression ratio in red as function of the water content for a number of different clays. And you can see already that most of the extension to compression ratios are below 0.5, which is off limits to the generalized Tresca criterion. So the best we could do possibly is to say that it's 0.5. That corresponds to a drain friction angle of 90 degrees, which is kind of not really all that credible sounding, and it would correspond to a simple shear to compression ratio of 2/3. So not exactly great fits, and kind of a bit dubious with respect to the implicitly assumed effective stress behavior. And if you look at this as well, I mean, there's quite a bit of data outside this, you could say, the credible range of 0.6 to 0.85. So the question is how to kind of make sense of that type of data, those types of materials with very low extension to compression ratios. And one of the ideas that people have had, so this is not really an original idea of mine, is to somehow look at the possibility that these materials may sometimes be anisotropic. The problem with introducing anisotropy, at least in the context of undrained shear strength, is that there's a huge amount of confusion out there in the soil mechanics literature, and I think it's fair to say in the soil mechanics community as a whole, as to what anisotropy really is. Sometimes it's taken to denote the situation where you have different properties in different directions, so say different strengths vertically as compared to horizontally. That's what I would call anisotropy. But sometimes it's also taken just to mean different strengths in extension and compression, which I hope I have sort of made the case has nothing really to do with anisotropy. That is a completely expected feature of a perfectly isotropic material. So, but of course, anisotropy could be part of the mix as well. So, but it's just important to keep these two effects separate. So just to sort of emphasize that this is to what I would call anisotropy, some sedimentary rocks where, of course, the anisotropy is a result of the of the sediments having been deposited vertically over time. And it's so anisotropy, this type of cross anisotropy as we see here, is of course by no means inconceivable when it comes to natural soils. And we took this rock and then compressed it vertically. Well, it wouldn't be too surprising if we had one strength when compressing it vertically and another strength when we compressed it horizontally. But of course, that has nothing to do with the fact that we would also have different strengths when compressing this vertically and extending it vertically, right? So this is the fact that these two extension compression strengths are different has nothing really to do with anisotropy. It's the same as if you compress a concrete cylinder, which is sort of an isotropic material, or you extend it. I've written here load angle. So for those of you who are familiar with this, this corresponds to a load angle of -30 degrees, so triaxial compression, and this is triaxial extension plus 30 degrees. So there's those two effects, a load angle effect, or you would say an extension compression effect, and that we have just covered. And then there is an effect possibly of anisotropy. But it's really important to keep these two things separate, and it's not always done. And one example where I think it's gone really quite wrong is the so-called NGI ADP model, which has given rise to a huge amount of confusion. So it's the model implemented in Plaxis, and it's kind of the model recommended for these types of materials. And it works in the way that you start with a Tresca criterion, a rounded Tresca envelope actually. I guess they have difficulty with sharp corners. So, but you start with a Tresca envelope, and then you see, well, you have equal extension to compression strength. That's not what you find. So then anisotropy is introduced by shifting the yield surface along the appropriate axis. So you sort of start with a wrong from a wrong starting point, and then you correct it by assuming something that is also wrong. So it's to emphasize again, extension to compression ratios less than 1 is a totally expected feature of an isotropic material. It has nothing necessarily to do with anisotropy. And so the predictions also, or the fits you would get with this NGI ADP model would be sort of less than optimal. This is the generalized Tresca fit, and then NGI ADP fit to the same data. So yeah, you match things in extension and compression, but everywhere else it's sort of a bit random what you get. So I think in order really to study the possibility that a material may be anisotropic, and I'm here looking only at cross anisotropy, so I've indicated that by these vertical, by these horizontal lines here, would be to, if you were to do it experimentally, I would go and take a large sample out of the ground and then cut smaller samples out of that large sample and then perform whatever test I had in my arsenal on that sample, Tri-Axial compression, extension, DSS, whatever. So fully characterize the sample for a particular orientation of the planes of anisotropy, and then you cut out a sample at some angle. I think this is about 45 degrees, do the same thing, and you go all the way around like that. And then you can look at how things differ, how the compression strength differs and how the extension strength and possibly the DSS strength differ as function of the orientation of the planes of anisotropy. And people have done that, at least with respect to compression. Here are some data, Boston blue clay, and this is that direction. This is the same kind of direction as I showed you here. So this is 0, this is 45, and this is 90 degrees. And we see that, well, there is an effect. So the sample is apparently stronger when compressed perpendicular to the plane of anisotropy than when compressed parallel to the plane of anisotropy out here. So that is, that's how that is for this particular clay. Now the question we had then was that could we try to, if we were to introduce anisotropy, how would we do it? Well, it would probably be too much to expect that these types of tests would, or results from these types of tests would be available. So one way of sort of doing it in a more practical way would be to assume that we have samples with this type of orientation. So they've been taken directly out of the ground. And then we have 3 types of results, 3 types of test results available: Tri-Axial compression, extension, and DSS. And can we then, by including anisotropy, make sense of these types of results in a better way? So very low extension to compression ratios, for example. And what we've chosen to do to try to make sense of that is to actually follow the NGI ADP approach of shifting this yield surface in this case, we call it the Z direction, the direction perpendicular to the plane of anisotropy, so this direction here. So if we are dealing with real physical anisotropy, that's somehow possibly kind of justified. It could be done in other ways. I'm not sure this is the best way to do it, but it's one way of doing it. And you then introduce, let's say, a 3rd degree of freedom. We already have the size of the yield surface and the shape of the yield surface from the generalized Tresca model. Now we also have the shift of the yield surface. So we have 3, you could say, degrees of freedom, or 3 internal parameters. And it turns out that they can be related uniquely to the three strengths measured in these three experiments: the triaxial compression, triaxial extension, and simple shear strengths. That's what we call the AUS model. So that's the anisotropic undrained shear strength model. It's a further development of the generalized Tresca model. And that extends the range of admissibility quite considerably as compared to the generalized Tresca model. So what I've shown you here is extension to compression on the x-axis, and then simple shear to compression on the y-axis. And the wide range here is the range of admissibility of the model. So you can pick any point within this wide range as input to the model. If you go for the isotropic version of the model, that is to say the generalized Tresca type version of the model, well, then the simple shear strengths are given in terms of the two other strengths, and that's on this red dashed line here. So you can then, it turns out you can then actually sort of improve things. You can postulate these variations of SUE to SUC and SUS to SUC as function of the water content. And if you look at the admissibility range chart, it corresponds to somewhere along the green line here. So, so this is quite useful in cases where you have very low extension to compression ratios, or alternatively in cases where you're lucky enough to have all three sets of test data available: compression, extension, and simple shear. But the model comes in also an isotropic version, which just requires extension and compression. And for sort of, unless for normal clays, let's say for clays that are not heavily anisotropic, I would think this is the way to go. And then if you have something special, so the LAD data would fit this, this would be appropriate for the LAD data. The Norwegian clays, you are sort of over here. Then you can do a virtual version of this test that I showed you before of cutting samples out of a larger sample, and I have some examples here. So this is the compression strength versus the inclination of these planes of anisotropy, and here I've assumed a simple shear strength equal to the mean of the compression and extension strengths, and then I've looked at what happens for different extension to compression ratios. And if we look at the 1.75 up here, which is kind of a standard ratio, then that looks actually not too far, at least qualitatively, from this kind of experimental data. So yeah, I think the model is quite capable and actually really quite credible. So that's how that is. Then this was so far everything I've talked about is to do with failure, but of course we want to say something about deformations as well, and I'd just like to sort of mention that very briefly. That's very much part of the AUS model as well. And what we have done is to basically construct an isotropic hardening model. It's not ideal, but it's not too bad either. So we have an initial yield surface that then hardens, that expands in response to shear straining out to a final or ultimate yield, or you can call it failure surface. And the hardening law, well, we have looked quite carefully at the work of Danica and Bolton, who have done some interesting work. They've taken a huge bunch of triaxial compression stress strain curves, and then they showed that if you normalize the deviatoric stress by the undrained shear strength and normalize the axial strain by the axial strain halfway to failure, when then these data tend to fall on more or less, not exactly a unique line, but there definitely seems to be a trend. And it's this trend that the hardening law that we use in the AUS model reproduces. And so one of the hardening parameters is this axial strain at half the strength. Flow rule, we could have used the associated flow rule, or the flow rule associated with this, whatever yield surface we have, the AUS yield surface. We have chosen to basically go for the Mises, for a Mises circle as the plastic potential. That tends to fit experimental data quite a bit better. These sort of yield plastic potentials with straight lines in principal stress space are not exactly great. So I think the Mises circle is not too bad. Here is again experimental data, failure points, the black dots here, and then the stress rates at failure, or the strain rates at failure, sorry, by the arrows. And you can see It's not perfect, but it's pretty good and definitely better than an associated flow rule in this case. And then finally, the shear modulus. So we need an elastic parameter. It's not that important unless you do unloading, and you can take it as some multiple of, say, your G50, which is related to the undrained shear strength and your strain halfway to failure. So that's the model. And again, there's an isotropic and an anisotropic version. That only relates to the strengths, and then the stiffness as well, an EU, or you could also a G, an elastic parameter, and then the strain at half the strength in compression and the strain at half the strength in extension. And there's typically a ratio of, well, here the default parameter is a ratio of 4, which is typically something of that magnitude you see from test data. So yeah, you can fit data really quite well. I mean, you're always sure to pass through the origin, of course, and then the halfway point, and then it sort of levels off. So there's a limit to how wrong it can go. I should say as well that there is actually a final parameter, we call it alpha, and it's a parameter that's in the vicinity of so say 0.5 to 0.7, and it's basically meant to tune the behavior at very small strain. So this is the second modulus versus the shear strain. And so if you're interested in the very small strain range, well, the model has some capabilities there as well. And extension to compression tests, or extension and compression tests, not perfect fits, but at least we of course we hit the strength, because that's very much an input parameter. And then finally, an example. I think I may have shown this before. This is one of the monopiles from the PISA project. This is a project that conducted full-scale tests on some fairly large monopiles. This is one of the ones from this project, and it was basically subjected to a horizontal load here up here at the top of the pile. And what was made available was undrained shear strength profiles. We interpreted these as compressive undrained shear strengths, and then we assumed on the basis of the drain friction angle, I believe it was 32 or so degrees, calculated an equivalent extension shear strength based on the formula that I showed you before. G naught or G max, so the small strain stiffness, and K naught, the earth pressure coefficient. So all this is input, direct input to the model. There's no need to go back and forth as you would do in, say, an effective stress model using, say, effective stress parameters. So that's one of the attractions, of course, of these total stress models, that you make direct use of the site investigation data. A plot of how things look close to failure, and then some load displacement curves, test results in blue, AUS in green and red. So this is for two different values of this strain at half the strength, 0.25% and 0.5%, and typical data are in that range, and both of them are kind of reasonable. In black here, some other results, finite element results with a completely different model, and an effective stress model actually, and at lower displacement levels as well. The green, the 0.5 seems to be better here, and at higher levels, well, the 0.25 seems to be better. But somewhere in that range, maybe 1/3 would have been, say, the optimal choice. And you can also look then at the effect. This is in terms of the failure load, the effect of the SUE to SUC ratio. And again, this is for assuming a simple shear strength equal to half the compression, to the mean value of the compression and extension strengths. Is the actual failure load and the normalized failure load over here. So here we are in a sort of a Tresca type material. And if we then move down to, say, 0.7 or so, we are at 80% of what we otherwise would have. And if we move even further down to sort of these very low extension to compression clays, well, there's a not insignificant drop in failure load. So this, I think, is something that is worthwhile taking into consideration, and it's something that can be done with this AUS model. If you have data from all three types of test, extension, compression, and DSS, well, then it's just simply inputting the data. If you only have extension and compression, well, then You can use the isotropic version of the model. And I should say, I would think it is always worthwhile to somehow assume, no matter what information you have, assume a reasonable extension to compression ratio, and that will always be less than 1. 0.7 would be my sort of default value of choice. And both these models, the generalized Tresca and the AUS model, is available in G2 and G3, and we have a paper as well finally out on this model in the International Journal. It's not written here, it's Numerical and Analytical Methods in Geomechanics, for those of you who would be interested in knowing more about the model. So with that, I will basically see if we have some questions. Are you still there, Jan?
Yeah, I'm still here.
Okay.
I think your camera is working now.
Okay. Yeah. I guess it is. I don't know if you can see me. Oh, okay. Okay, so let's move to the questions. There's a lot of chat questions. I don't know if you've been following those, Jan.
Yes, yeah, I have. So there is actually one of the things that's been asked one of the questions that's coming up is what kind of clays does this apply to? So when can you use Tresca? Is Tresca a good? Is it sometimes a good model? I mean, you already showed it in the diagram with the plasticity index, right, versus the ratio. So it's really not to say, right? I mean, sometimes it's good, sometimes it's bad model to use Tresca, I guess.
I mean, the standard Tresca is always bad to use, but what we call the generalized Tresca, which allows you to have different extension and compression strengths, that is, see, let me share my screen again. So the isotropic version of the model, basically, this version of the model over here, where you have an compressive SuC, compression strength, and then a ratio extension to compression. I would think that sort of would be the default model to apply if there's no sort of significant anisotropy, which is sort of our default position. We know that there is always probably a bit of anisotropy, but most of the time for whatever material we're looking at, we assume that it's more or less isotropic. Then this is the model I would be that I would use. And so for the data here, the lab data, this model works absolutely fine, right? It's fine. If you have then more unusual extension to compression ratios, much lower extension to compression ratios than 0.5, well, that could be or that's kind of consistent with the idea that there's anisotropy at play, and then of course it's the full anisotropic version of the model that should be applied. So this one here, where you have the three strengths,
exactly,
both compression, extension, and simple shear. So, but I would, yeah. So that's what I can say to that. I hope that makes sense. Then there's a question, what about offshore cohesive soils? Yeah, I mean, this is kind of part of the motivation was actually offshore, the kind of clays you find offshore. So I would think this model here, and I know it's been used for that, I would think this model is exactly what you need for those types of soils. So absolutely. And then there's questions about quick clays and softening and so on. And I have to probably disappoint here a little bit that there is no softening here and there's no effects. The quick clays would be, I mean, are very, very strange clays, right? So there's no softening included here. We may add that at some stage, but it introduces a whole range of other complexities and other questions that I think the modeling of softening in a finite element context is to some extent still a bit of an unsolved problem, but it's something that we look at from time to time and that we have some ideas of how to include, so we may do that.
Yeah, there's a good question here, Kristian. There's something that you mentioned briefly in the introduction. So could you, for which practical problems is it relevant, or does it have a larger relevance to include, let's say, the generalized Tresca with a different compressive and tension on shear strength?
So sure. So that's what I kind of tried to give a flavor of here with this tunnel phase stability problem, that that if we are dealing with the problem of determining the necessary pressure to keep this tunnel phase stable. So we're basically looking at the situation where the tunnel phase collapses into the tunnel, right? So it's a kind of an active earth pressure problem. Well, then it turns out that the extension to compression ratio has really a fairly pronounced effect, right? So there's a lot of extension going on in this problem.
Yeah.
And if you have a smaller extension than compression strength, well, then that's gonna have an effect. Whereas the passive version of the problem, where basically this, where we over pressurize the tunnel head so that we have a blowout, we have a connection, we blow this out to the top surface. So it's a kind of a passive type problem where that's kind of dominated by compression. Well, then it means a lot less, and in this case, it actually means absolutely nothing. So it's really problem dependent. I would say slope stability problems, it can be important as well. 3D slope stability problems, excavations, these problems, it's not insignificant at all. And of course, embankments and these types of problems as well.
Okay.
So, yeah.
What if you?
Yeah.
What if you add or include anisotropy on top of that? When does that come into play in terms of relevance? So now we're talking about an isotropic material here in this tunnel phase stability blowout.
So the AUS model, I mean, I didn't sort of maybe explain that properly, but the AUS model, the AUS model is designed so that so you have these three strength parameters: the extension, compression, and simple shear. So the extension and compression will always have to enter into the model, and the fact that these are different doesn't necessarily indicate any amount of anisotropy. But if you then you then enter a simple shear strength as well. Now that simple shear strength, the model is constructed so that if anisotropy is necessary to make sense of these three strengths, then the model will be anisotropic. Otherwise, it will remain isotropic. So um, so
Okay.
let's say there wasn't a much better explanation. I had this example here. So if we were to enter a undrained compressive strength of 100, extension 60, and a simple shear strength of 75, well, that corresponds to what we would have with an isotropic material. So in that case, there is no anisotropy induced at all.
Yeah.
So I would say anisotropy really comes into play when you have these very extreme extension to compression ratios, like we saw for those Norwegian clays, where it's down to 0.2, 0.3, something like that. Then anisotropy is necessary in order to really make sense of that data. So that in that case, it's necessary with this shift of the yield surface in the Z direction.
Yeah. So in most cases, the isotropic model will actually, the generalized Tresca will do the job quite nicely. Except
yes,
in extreme
yes.
cases, that's a kind of what
that is my opinion. Yeah.
Yeah. Very good.
That data with sort of with a moderate ratio between extension and compression, and then the DSS ratio in between, that there's no need to introduce anisotropy to explain that.
Fantastic.
That's a good question. Stiffness anisotropy. And well, the answer is and it's maybe a bit sort of unsatisfactory, but the answer is for the AUS model, the answer is no. It's actually the elastic part, the elastic behavior is isotropic. But if you're interested in elastic anisotropy, which in some cases may be important as well, there is in G2, we don't have it in G3 yet, but there is for all materials in G2, there is the possibility when it comes to the elastic law, we have these different parameter sets, A, B, and there's one called nonlinear, and then there's one called Graham-Holsby. That's this anisotropic model from these two guys, Graham and Holsby, which allows you to basically make a distinction between the Young's moduli in the two directions, vertically and horizontally. So that's what I can say about that. It will be included in the AUS model as well. It's just to keep the number of parameters kind of fairly limited, and in most cases, from what we can see already, this stiffness anisotropy doesn't really have a huge effect. It's the strength anisotropy that really is the important part. Can the model be used for excavation problems? Yes, absolutely. I would say it's very relevant for excavation problems where, of course, you have behind your retaining walls, you have active earth pressures and those, so you're in kind of a state of extension. So I would say it's very relevant for extension problems.
Yeah, then Matthias is asking, how does it compare to Plaxis? Do you want to answer that, Kristian? This is a very general question.
Yeah, I mean, I can say definitely the Plaxis equivalent of the AUS model is the model I just briefly mentioned, the NGI ADP model, which is a problematic model because it introduces anisotropy to account for a feature which is a completely expected and uncontroversial feature of an ideal isotropic material. So that is, and you can see the kind of implications that has. Not fantastic. So
can you just what you're saying is that the red line here is how the NGI ADP model would fit to the data.
That's right. Yes.
The blue dots. And
yes.
why is it not fitting better?
Why is it not fitting better? Because the basic assumption behind this model that the yield surface is a kind of a Tresca hexagon is wrong.
Yeah.
It's not a Tresca hexagon. It's a kind of a Coulomb type cross section that actually is at play here. So this base assumption of a Tresca hexagon is wrong. And then in order to sort of correct it in the best possible way, anisotropy is introduced, even though the material may well be completely isotropic. So it's sort of two wrongs to make a not very good right that is attempted. So I would say that's not a very good model at all, and I would doubt the results from it myself. I would say this is something I would stay away from. Optum and Plaxis in general, well,
I think you're falling out.
Programs are very similar, so it's geared towards the same kind of. Oh.
No, it's I think it's the connection. So.
Yeah, so I was saying in terms of the programs itself, generally speaking, Optum and Plaxis are similar in the way that they cater for the same type of applications or the same type of geotechnical problems. So I don't see many differences there. I think the main difference between the two programs is user friendliness, and especially user friendliness when it comes to robustness of the calculations. And both robustness in terms of, you could say, convergence and these types of things, and also in terms of actually getting accurate results and the ability to, in Optum, to verify the accuracy of your results using the upper-lower bound methodology that we have talked about before in previous webinars. So all in all, I think that gives a much quicker workflow, and in sort of engineering practice, it would give, I think, quite a significant boost in productivity. So,
that's good. And Mateus, you're asking about general modeling capabilities, pre and post processing. I mean, it is a general purpose geotechnical fine element program like Plaxis. Plaxis have Plaxis 2D and 3D. We have OPTUM G2 and G3. And like Kristian said, the main difference in terms of the calculation core is that Optum has limit analysis as well as FEA, so which is a very powerful mixture. But the best thing really to make your own opinion about it is to go and download the software. It's easy to get a free trial version. And feel free to contact us while you're testing if you have any problems, and we'll be very happy to assist you.
Yeah.
Should we have one last question, Kristian?
Yes, if there is one.
There is something with a pipeline. I don't know how relevant that question is. Something with, no, it's not. Okay, maybe we should call it a day then. It's also just hit 5 o'clock. Yeah, okay. Thanks for listening in. We will send the an email around as we usually do with the link. And also we'll be sure to send around the link to the webinar next week, which I really hope that you'll be able to make. It's going to be very interesting hearing how Subsea 7 have used OPTUM G3 and use it in their everyday work. And then there was a question about the PowerPoint file just coming up here, and sure, I will put a link to that also when I send round the mail here. Okay, take care everyone, and hope to see you next week.
Yeah, thanks for joining, and yeah, see you next week. It should be a really interesting one. So, yeah.